Anticipation filled the air as they witnessed the long-awaited activation of the most advanced high-energy particle collider. After patiently waiting for decades, they finally beheld this remarkable invention poised to transform our comprehension of the universe. The Large Hadron Collider, constructed by the European Organization for Nuclear Research, became operational in September 2008 after a painstakingly protracted construction phase. However, it took the machine's inventors several years to perfect it. Since then, the Large Hadron Collider has played a pivotal role in unraveling numerous enigmas of the universe during its various experimental runs. Nevertheless, recent developments have raised concern among scientists at CERN. Upon ramping up the Large Hadron Collider to a new peak energy level, they detected something unexpected and terrifying. Subsequent investigations have led to various theories attempting to explain this phenomenon, but as of now, they remain unverified and speculative. The universe has many unexplained mysteries, and over the years, scientists have devoted their time to research in an attempt to understand and explain some of them. These mysteries include the massive black hole found in space, which is said to have an intense gravitational pull that even light cannot escape, and also what lies underneath the Bermuda Triangle, called the Devil's Triangle. It is popular for the mysterious disappearance of more than 50 ships and 20 aircraft, but they remain unexplained due to limitations in technology. In the early 20th century, physicists looked for new ways to explore the fundamental building blocks of matter. In 1932, physicist John Douglas Cockcroft and engineer Ernest Walton constructed the first operational particle accelerator. These particle accelerators are essential tools for exploring the fundamental constituents of matter. By accelerating particles to high energies and colliding them, scientists can study the resulting interactions and probe the fundamental forces and particles that make up the universe. Given how useful particle accelerators can be in explaining the mysteries of the universe, CERN has constructed the world's largest particle accelerator. But scientists have just made the horrible discovery that this particle accelerator would likely cause the Mandela effect because of its ability to alter the fabric of space and time. What is the implication of this discovery? Many people wonder why they remember things differently from how they happened. Well, this is a phenomenon known as the Mandela effect. The term was coined in 2009 by Fiona Broome. She found out that she and many others wrongly thought Nelson Mandela had died in the 1980s, but he died in 2013. Several factors can cause this effect, such as false memories and the strong influence of social media and the internet. But certain scientists have raised concerns that previous power-ups of the LHC have also caused the Mandela effect. Before dismissing this discovery as a conspiracy theory, note that some prominent scientists and other notable figures have raised concerns. Stephen Hawking was one of the first to express his concerns about the effect of the Large Hadron Collider. He warned in an interview that the collider could create black holes, which could threaten the universe. Another scientist, Dr. Carlo Relli, shared his concerns about the LHC in a blog post, suggesting that it might create strange particles, hypothetical particles that can change surrounding matter into something new. Even figures outside of science have spoken about the potential dangers related to the Large Hadron Collider. Astrophysicist Carl Sagan and science fiction writer Arthur C. Clarke also voiced worries about the collider, suggesting the creation of strangelets or even a black hole that could swallow the Earth. In a press conference, President Obama also expressed his concerns about the collider causing a catastrophic event that could affect space and time. The fact that several groups of important people, from scientists to writers and public figures, expressed unease about the LHC highlights the seriousness of the concerns. While we can't predict the consequences, it's crucial to carefully consider the potential risks and make informed decisions about operating the collider. So, is CERN's LHC capable of causing the Mandela effect and other changes in our universe? The Large Hadron Collider is currently the biggest and most powerful particle accelerator in the world. It was built between 1998 and 2008 in collaboration with over 10,000 scientists across more than 100 countries. It became operational on September 10, 2008, and is the newest part of CERN's accelerator complex. The goal of this particle accelerator is for physicists to test the predictions of different theories of particles, including measuring the properties of the Higgs boson, searching for the large family of new particles predicted by supersymmetric theories, and studying other unresolved questions in particle physics. The collider looks like a 27-kilometer circle that is made of strong magnets and structures that make particles go faster and gain more energy. Inside the accelerator, there are two beams of high-energy particles that move at an incredible speed, almost as fast as light, before they are directed to collide. These beams travel in opposite directions through separate tubes called beam pipes, which are kept at extremely low pressure. The beam pipes then follow a circular path around the accelerator due to a powerful magnetic field generated by the superconducting electromagnets. The magnets are made from coils of special electric cables that operate in a superconducting state, allowing electricity to flow without resistance or energy loss. To maintain this superconducting state, the magnets need to be cooled to a temperature of -271.50 degrees Celsius, which is colder than outer space. To achieve this, a system of liquid helium is used to cool the magnets along with other necessary air supply services throughout the accelerator. Running at an energy of 6.5 TeV, tera-electron volts, per proton, the LHC accelerates protons from 450 GeV, giga-electron volts, to 6.5 TeV during this process. The magnetic field of the superconducting dipole magnets increases from 0.54 to 7.7 teslas. The collision energy of the protons reaches an impressive 13 TeV at this energy level. The protons attain a Lorentz factor of about 6,930, moving at a velocity of approximately 0.999999990 times the speed of light. The time it takes for a proton to complete a full orbit around the main ring is less than 90 microseconds, resulting in an astonishing 11,245 revolutions per second. The journey of protons in the LHC begins in a linear particle accelerator, LINAC-4, that generates negative hydrogen ions at 160 MeV, mega-electron volts. These ions then move through the proton synchrotron booster, where electrons are stripped away, leaving only the nucleus with a single proton. Subsequently, the protons are accelerated to 2 GeV and enter the proton synchrotron, reaching an energy of 26 GeV. Finally, the superproton synchrotron boosts its energy to 450 GeV before its injection into the main ring. In this ring, protons are accumulated, accelerated to their peak energy over 20 minutes, and circulated for 5 to 24 hours, allowing collisions to occur at the 4 intersection points. While the primary focus of the LHC physics program is proton-proton collisions, it has dedicated periods, typically 1 month per year, for heavy ion collisions. Lead ions are the preferred choice for this program and are accelerated to an energy of 2.3 TeV per nucleon or 5.02 TeV per ion in the LHC ring. The LHC operates with a significant amount of energy and generates massive data collections, demonstrating the enormous size and importance of this scientific effort. The CERN site draws approximately 200 megawatts of electrical power from the French grid during LHC operations, roughly 1/3 of the energy consumption of the city of Geneva. Notably, the LHC accelerator and detectors contribute around 120 megawatts to this demand. This energy surpasses that achieved by the relativistic heavy ion collider. The heavy ion program aims to explore quark-gluon plasma, a state of matter believed to have existed, providing unique insights into the fundamental nature of matter and the cosmos. With the help of this particle accelerator, one of the major theories in particle physics concerning the existence of the Higgs boson particle has been proven. The Higgs boson, often referred to as the God particle, made its appearance at CERN in 2012, marking a significant breakthrough in the field of particle physics. If you're wondering how the Higgs boson particle earned its nickname, it's from a book titled The God Particle, written by Leon Lederman in 1993. However, this nickname has faced several criticisms from many physicists due to its potential to mislead the public. The Higgs boson is a subatomic particle in the Standard Model of physics, produced by the activation of the Higgs field. In the Standard Model, the Higgs particle is a massive scalar particle with zero spin, even parity, no electric charge, and no color change that interacts with mass. The particle is also very unstable, disintegrating into other particles almost immediately upon its generation. The Higgs field, shaped like a Mexican hat, is an invisible force field with different parts that are both electrically charged and not electrically charged. This special field affects the way particles interact, giving them mass through something called the Higgs mechanism. The Higgs particle and its field are named after Peter Higgs. In 1964, this physicist, along with 5 other scientists, proposed the existence of the particle, which is the only explanation for why some particles gain mass. After searching tirelessly for 40 years, scientists found a particle with the same characteristics as the proposed Higgs boson in the LHC. Finding the Higgs boson as predicted was very important because the particle is crucial to helping us understand why some particles have mass, a basic property that affects how stuff behaves and explains how things in the world interact with each other and make up the fundamental building blocks of matter. To create Higgs boson particles, scientists make use of 2 beams of particles and make them crash into each other really fast. Sometimes, a Higgs boson is created as a part of this collision, but it doesn't last long because it decays quickly. Since the Higgs boson disappears quickly, scientists can't see it directly. Instead, they look at all the things created when it decays, and from that, they figure out the decay process. If what they see matches what they expect from a Higgs boson, it suggests that a Higgs boson might have been made. However, making a Higgs boson in a collision is rare, and many other collisions can look similar. So, scientists have to analyze data from trillions of collisions to be sure. They need to see the same pattern on 2 different detectors and analyze it to make sure it's not just random background events. Extensive scientific research has been done to check if there are connections between the Higgs field and the Big Bang, a hypothetical field proposed to explain the rapid expansion of space during the universe's early moments. Some theories state that a fundamental atomic field, such as the Higgs field, could be responsible for this phenomenon. The fate and nature of our planet have become subjects of exploration because, according to the Standard Model, there's a possibility that the state of the universe, known as the vacuum, might last for a long period of time but is not particularly stable. This means that there is a chance that the universe could become more stable in the future, which would alter everything that we believe in and have come to understand about the universe. The masses of the Higgs boson and top quark are important in determining the stability of the vacuum that houses the universe. If the universe is in an unstable vacuum, it could lead to significant changes in the distant future. There is the need to accurately measure the mass of the top quark by using a special kind of collider that is known as the electron-positron collider to figure out what would eventually happen to the universe in case the stability of the vacuum should change in the future. Scientists also believe that the Higgs field is the energy that fills up the vacuum, influencing the extreme energies of the universe's early moments. This idea suggests that the Higgs field went through different changes in structure over time and in the process created the forces that we see in the universe. Scientists are currently studying the Higgs field's connection to the energy in the empty space of the universe. The energy found in space right now is very close to zero, but theories involving the Higgs field and other ideas suggest it should be much higher. This difference creates a big unsolved problem in physics called the cosmological constant problem. Looking back at history, we can see how particle physics has developed our understanding of the basic building blocks of matter and forces. In the 1960s, scientists had a tough time trying to bring together the electromagnetic and weak nuclear forces using quantum field models. The theories they had, like Yang-Mills theory, predicted that certain particles which we knew had mass should actually be massless. This caused a big problem. There was also a theory called Goldstone's theorem that suggested the existence of particles with zero mass called Goldstone bosons, and that added to the challenges. At first, scientists didn't pay attention to the theory, but it eventually became extremely important after 't Hooft and Veltman made significant progress in fixing issues with the Yang-Mills theory. From 1971 to 1972, their work and ideas from the renormalization group and Russian physicists strengthened the theoretical basis. Even though people weren't interested in it initially, the theory became very popular and widely accepted, changing the way we look at particle physics. Scientists are studying the Higgs field in various ways, from its possible involvement in the Big Bang to how it affects the stability of the universe and its connection to vacuum energy. Looking back at history, we see scientists working hard to uncover the secrets of the basic pieces that make up the universe. Their efforts have resulted in theories and models that help us understand the cosmos better. Quantum field theories, which are based on a concept called gauge invariance, have done really well in understanding forces like electromagnetism and the strong force. But in the early 1960s, when scientists tried to create a theory that included both the weak force and electromagnetism using gauge invariance, they ran into a lot of problems. These difficulties made physicists feel stuck and unable to create a complete theory for particle physics at that time. As a result, gauge theories lost some of their good reputation. The issue came up because the predictions for the weight of the weak forces particles, W and Z bosons, said they should have zero mass. In particle physics, mass refers to how heavy a particle is when it's not moving. But when scientists did experiments, they found that W and Z actually have some weight, which is a direct contrast to what they predicted. Additionally, possible solutions seemed to require the presence of extra particles known as Goldstone bosons, yet there was strong evidence indicating that these supposed particles might not be real. This left physicists with a puzzle. Either the approach of gauge invariance was wrong, or there was some unknown factor giving weight to the weak forces W and Z bosons without creating Goldstone bosons. By the late 1950s and early 1960s, scientists were confused about how to tackle these problems and create a complete theory for particle physics. Hadrons are also important in understanding how these quarks interact. When new hadrons are discovered, it gives us real-world information about how quarks behave in extreme situations. This data helps improve our theoretical models. By closely studying the characteristics and actions of these newly identified particles, scientists hope to uncover the mysteries of the strong force and gain a better understanding of the complex interactions between quarks and gluons. Additionally, studying hadrons at the LHC has helped scientists to expand and understand the Standard Model of particle physics. The Standard Model has been good at explaining many things, but it's not a full theory. There are still things it doesn't have an explanation for, like what dark matter is, how fundamental forces come together, and why there's more matter than antimatter in the universe. Investigating this strong force with hadron studies is an important step in being able to explain some of the mysteries in the cosmos. Finding the Higgs boson has given scientists new paths to explore in particle physics. They're still looking into how it acts and what it's like, hoping to find differences from what the Standard Model predicts. If they can understand the Higgs boson more deeply, it might uncover things we don't know yet and push forward our understanding of theoretical physics. As scientists continue to study this strong force, they believe that the information they gather will not only explain how tiny particles interact with each other, but also lead to innovation and advancement in technology. While there is no scientific fact to prove that the Large Hadron Collider is responsible for the Mandela effect or can even create cosmic black holes, it is important to note that while the LHC is a powerful invention that can be used to solve several cosmic mysteries and help us understand the planet we live on better, unnecessary inferences of this particle accelerator in the cosmos can also have negative and irreversible impacts on our planet.